Chain of events, cause and effect. We analyze what went right, what went wrong, as we discover that many outcomes can be predicted, planned for, and even prevented. I'm John Chidgey, and this is Causality. Causality is entirely supported by you, our listeners. If you'd like to support us and keep the show ad-free, you can by becoming a premium supporter. Premium supporters have access to high-quality versions of episodes as well as bonus material from all our shows not available anywhere else. Just visit engineer.network/causality to learn how you can help this show to continue to be made. Thank you. Callide C Blackout. Just outside the city of Biloela in central Queensland, Australia, in June 1965, the first 30-megawatt generator came online at the still then under construction Callide coal-fired power station. Due to a prolonged drought and losing a generator at sea, as it was transported from England, the Callide power station originally didn't reach its full 120-megawatt output until May of 1969. The power station was fed from coal via an overland conveyor from the Callide open-cut coal mine, with cooling water sourced from the Callide Dam, though in recent years it has been transported from the Awonga Dam via pipelines due to demand growth. During the 1980s, a series of 3 major baseload power stations were built in close succession in the surrounding area in Queensland. Tarong, consisting of 4 350-megawatt generators totaling 1,400 megawatts, Callide B, consisting of 2 350-megawatt generators totaling 700 megawatts, and Stanwell Power Station, consisting of 4 360-megawatt generators totaling 1,440 megawatts that I personally worked at for 6 months in 1996. The original Callide Power Station was retrospectively renamed Callide A and continued operating until 2001, after which it was shut down, given the age and small capacity of the plant by comparison at the time. The newer Callide B power station produced significantly more power, and during 2001, the newest Callide C Power Station was also brought online. The Callide C Power Station also consisted of 2 units. However, these were 424-megawatt units, totaling 848 megawatts. Each unit between Callide's B and C power stations is numbered incrementally across both, but not alphabetically, leading to the somewhat odd numbering system. Units B1 and B2 for Callide B, and units C3 and C4 for Callide C. Callide B is owned and operated by CS Energy in totality, whereas Callide C is owned by a joint venture, JV, between CS Energy and Intergen, or IG Power, though CS Energy operates both plants. It's worth noting that CS Energy is a state government-owned corporation. Callide Power Trading Proprietary Limited, or CPT, trades the output of the Callide C plant on behalf of the JV. When it was constructed, Callide C was the first supercritical coal-fired power station to be built and operated in Australia. Unlike traditional coal-fired power station boiler systems, supercritical power plants have a higher pressure-rated boiler to operate at temperatures and pressures that reach water's critical point. A brief aside about materials. When a material is heated to a certain temperature and pressure, it passes from solid to liquid, and then to gas, and eventually to plasma. But at the so-called critical point, the gaseous component cannot be liquefied by applying more pressure, and the liquid cannot be pushed into a gaseous state by increasing its temperature either. This results in a supercritical fluid that is, helpfully, neither a liquid nor a gas, but has the properties of both at the same time. Weird, but cool. The critical point of water, H2O, is 374 degrees Celsius or 705 degrees Fahrenheit and 22.06 megapascals. And in the past 30 years, materials science has been able to produce more affordable piping systems that can accommodate these high temperatures and pressures such that boilers can run safely at supercritical temperatures and pressures. A simple question though, why do this at all? The basic Rankine cycle of a thermal-electric plant consists of 4 stages in a continuous sequence. Heating of the fluid in question until it's a gas, expansion of the gas in a turbine creating rotation and performing work, condensation of that vapor exhaust from the turbine back into a liquid, and pumping or return to the heating stage, since it is unfortunately not possible to pump gas, though you can pressurize it and make it flow, but that's another story, thermodynamics and all that. Anyhow. The amount of energy able to perform work has traditionally been limited to about 33% overall energy conversion efficiency due to boilers and pipework material limitations. However, with recent material science advancements, operating at higher temperatures and pressures now makes it possible to exceed this. Several supercritical plants have achieved 44% overall efficiency in operation, with some experimental plants creeping up towards 50% efficiency. More efficient, less energy is wasted, seems like the way to go. Having said all of that, it's more of an aside for this incident, as the fact it was a supercritical plant plays no part in the outcome. So let's get back on topic. The electrical systems at Callide C were flagged as requiring an upgrade of the 220-volt DC battery chargers, and in late 2019, an upgrade program was launched internally to replace the existing battery chargers for the 220-volt DC battery systems. There are 3 220-volt DC battery systems in the Callide C plant, one for each unit, and a common or system battery. The DC power supply is used for unit control, monitoring and protection power supply, and also for emergency backup for lube oil or lubrication oil, and generator coolant gas, sealing oil. The battery backup allows critical systems to function even if AC from the generators and the grid become unavailable for whatever reason. There are also 3 6.6 kV AC switchboards, one for each unit and one for the common station board. At Callide C, there are only 2 6.6 kV transformers, one for each unit, with the station 6.6 kV board fed from either unit board. With that background, let's talk about the incident itself. On Monday, the 24th of May 2021, at 2:08 p.m. local time, Unit C4's DC battery charger was energized and connected directly to its battery string in offline charging mode to ensure the batteries were at a maximum state of charge ahead of the following day's planned work to switch over the new battery charger to fully online operation. By approximately 8 p.m. that evening, the battery string in Unit C4 was indicating that it was fully charged. On Tuesday, the 25th of May 2021 at 1:28 p.m., the C4 battery string was isolated from the DC charger and remained disconnected from the main DC bus. The station DC bus and the Unit C4 DC bus were both connected via the DC bus interconnector that had been in place whilst the C4 battery string was offline charging on the previous day. At 1:31 p.m., the Callide C4 unit was operating steadily and producing 278 megawatts of power to the Queensland State electricity grid via the Calvale substation. At 1:32 p.m., the Unit C4 DC battery charger was reconnected to the main DC bus. At 1:33 p.m., the command to open the interconnector was given, and the Unit C4 DC main bus and DC distribution board buses rapidly dropped to nearly 0 volts. They went dead, or rather the voltage decayed from about 240 volt DC to 10 volts DC in only 3 seconds, since inductance and capacitance in cabling and equipment stops an instantaneous voltage change. Within 2 seconds, the 415 volt and 6.6 kV auxiliary systems upstream circuit breakers all tripped, and since the 6.6 kV bus for the common station bus was being fed via Unit C4's 6.6 kV board, both the station and Unit C4's 6.6 kV and 415 volt AC boards all went dead. Within 2 minutes, the DC bus voltage drop had led to a turbine trip that closed the steam supply valves to Unit C4, an excitation system trip, and the generator protection systems all became inoperable. The loss of the auxiliary power had subsequently led to a loss of turbine lube oil, loss of generator seal oil, a boiler trip, and loss of all control room screens for Unit C4. The alarm screens that were still working at their peak were experiencing severe alarm flooding with over 15,000 alarms during the incident period, and the operators were unsure which of them could be trusted without the SCADA system to validate the plant's state. At 1:34 p.m., the emergency diesel generator, or EDG, automatically started upon detecting loss of voltage on the 415 volt AC auxiliary board and was up to speed and ready to connect 25 seconds after power loss detection, as designed. However, the lack of any 220-volt DC power meant that the circuit breaker close command required to re-energize the Unit C4 415-volt emergency board could not be executed, and the generator closed onto the station emergency board, and that was it. Unit C4 remained electrically dead. Since the generator circuit breaker couldn't trip, the generator remained connected to the grid, and without an energy source to drive the motor generator set in forward generation, it shifted to forward motoring. Essentially, the generator became a huge asynchronous motor. Since there was no rotor excitation, it was being driven by grid power, now drawing power from the grid instead of supplying power to it. It was now also running without any cooling systems, lubrication systems, or protection systems of any kind, and for the next 30 minutes, temperatures rose out of control, which included excessive heat in the bearings. Keeping in mind the entire turbine generator set is physically linked, hence the rotation was also being applied all the way back through the turbine blades as well. Without generator seal oil, hydrogen gas began leaking out under high temperatures and was ignited either by high temperatures, greater than 570 degrees Celsius or greater than 1050 degrees Fahrenheit, or electrical arcing, causing multiple small explosions in the minutes following the trip. At 1:40 p.m., CS Energy contacted AEMO and advised that there was a possible fire at Callide Unit C4 and they were continuing to investigate. By 1:43 p.m., all of the hydrogen coolant gas had completely leaked out of the generator, leaving the generator uncooled. The bearing's outer surface had been severely degraded due to the extreme heat, allowing the shaft to flex as it was rotating, with temperatures in the shaft reaching 730 degrees Celsius or 1350 degrees Fahrenheit. At 1:44 p.m., Callide Unit C3 also tripped, and CS Energy again contacted AEMO to confirm there was a fire in the Callide C unit hall. At this time, the AEMO Energy Management System, EMS, showed that C4 was sinking 50 megawatts and 300 megavars from the grid, though the line voltage of 275 kV at the Callide substation was still holding. At 1:49 p.m., the Callide control room was evacuated to ensure the safety of personnel. At 2:04 p.m., a small number of operators and technicians were cleared to return and re-entered the control room in Callide Unit C4. At approximately 2:05 p.m., a technician managed to restore some power to the control room computers and screens for Unit C4. However, the displayed SCADA information was conflicting. The control room operators were still unclear if the steam valves were open and were still connected and driving the turbine. They were concerned that if they asked PowerLink to disconnect from the grid without the grid to work against, the generator would accelerate into an overspeed condition and tear itself apart. At 2:06 p.m., the generator, or rather now a motor, and its connected turbine blades were now flexing so much the blades started catching on the turbine housing. The blades quickly eroded the impacted metal turbine housing in 9 separate locations and sent shrapnel at high velocity through the turbine hall as the turbine catastrophically failed. A 2-ton steel shaft segment flew 5 meters from the turbine, and debris was launched 20 meters into the air, punching holes through the roof of the turbine hall. The generator was now experiencing high temperature arcing between the rotor and the stator, ionizing the copper, and was now sinking 300 megawatts and 1400 megavars from the grid, which was 3 times its actual power rating. This dragged down the line voltage at Callide substation, resulting in reactor and capacitor banks being switched in to compensate. Callide Unit B2 then also tripped. After 40 seconds of arcing in Unit C4, a phase-to-phase fault dropped the A and B phase voltages severely at the Callide substation. The following events happened in a time span of less than 60 seconds. Stanwell Power Station, Units 1, 2, and 4 all tripped on low system voltage, and further north, the Townsville gas turbine ramped itself down to 0 megawatts. All of the 275 kV lines out of the Callide substation tripped at their respective remote ends. The Callide substation feed breaker, number 854, from Unit C4 opened, finally isolating the generator from the substation. Unit C4's final motoring load was measured at 57 megawatts pulled from the grid before the substation eventually tripped, after which it slowed and stopped. The power flow shifted from existing baseload plants to the Queensland-New South Wales Interconnector, or QNI, peaking at just over 1 gigawatt, noting that nominal power flow is 600 megawatts on QNI, before automatically tripping for 16 seconds and then automatically reclosing again by design. This interruption pushed the Gladstone Power Station Units 2, 3, and 4 to trip, and with the Queensland grid now isolated, the base frequency shifted to 48.53 Hz, which then started under-frequency load shed relays throughout the state that started triggering at frequencies less than 49 Hz. It's worth noting that the nominal system frequency in Australia is 50 Hz per European standards, unlike the United States, which operates at 60 Hz. The new power system load reduction was approximately 2.275 gigawatts in Queensland and 25 megawatts in northern New South Wales. By 2:07 p.m, the grid frequency had stabilised to 50 Hz and the QNI was reconnected. At 2:10 p.m, AEMO gave permission to commence load restoration from loads that were shed due to under-frequency relay operations. AEMO also gave permission for all available units to resynchronize to the grid and reconnect, with Yarwun Cogen reconnecting at 2:28 p.m, Stanwell units starting at 2:31 p.m, and the Gladstone Power Station unit starting from 2:52 p.m. At 3:03 p.m, the Callide substation was re-energized, and by 3:40 p.m, all 275 kV feeders were reconnected. The outage had impacted somewhere between 375,000 and 475,000 premises, based on which report you read, with a total of 2.3 gigawatts of net load interruption, tripping 9 generator sets across the state of Queensland. No personal injuries or fatalities occurred in this incident. Let's talk about the investigation. Following the incident, CS Energy engaged Dr. Sean Brady, a renowned Queensland-based forensic engineer who recently completed the so-called Brady Review, investigating the causes of fatalities in the mining industry in Queensland in 2020. They also engaged an engineering firm, Oricon, and other specialists to assist Dr. Brady and to publish their own lessons learned report. In addition, Workplace Health and Safety Queensland and the Australian Energy Market Operator, AEMO, both launched their own investigations. Research for this episode is based on the Technical Investigation Summary published by CS Energy on the 13th of February 2024 and AEMO's report from October of 2021. These reports are separate from Dr. Sean Brady's independent investigation, whose report release date is as yet unknown. CS Energy created a video animation of the incident that clearly depicts what happened based on their findings, and despite a small number of discrepancies between the video and the released report, it is a high-quality illustration of what happened physically. I'd strongly encourage you to watch it if you want to see the events described more pictorially. The fault tree provided in the CS Energy report has two main branches that led to the failure to disconnect from the grid and the failure of the lubrication system. My only issue with this is that if you play out a scenario where lube oil was still running, the cooling gas would still have leaked out, leading to overheating of the generator. It just would have taken longer before final failure occurred. This would have allowed more time to disconnect from the grid or minimize the damage, but not prevent recovery from the incident without damage. Even though the local breakers were inoperable, at any time, the Callide substation breaker could have been opened. During the investigation, it was determined that AEMO and PowerLink were ready to isolate the Unit C4 from the grid as soon as CS Energy requested them to do so. However, the request was never made. There's a lot to unpick here, so let's start with what happened with the DC power system. Starting with the chargers. DC battery chargers aren't meant to work in parallel all the time, but when they are put in parallel, the one with the highest set output voltage will bias all of its power to the load, whilst the other will limit its output down, eventually being limited to 0 amps of current output in certain circumstances. This is to prevent one charger from damaging the other charger or chargers that are interconnected. To ensure the preference is for the unit DC battery charger to supply the bus, it should have been set to a slightly higher voltage than the station charger. However, the station charger's output was set higher. Based on the information in the reports available, it's unclear why this was set in this manner. However, in the press conference Q&A, it was stated that this was set during the original design. 74 seconds prior to the interconnector opening, when both chargers were operating in parallel, the Unit C4 charger was not outputting any current. Hence, when the interconnector was opened, the DC Unit C4 main bus went effectively dead. One wonders why the command to open the interconnector was given, seeing as how the charger wasn't outputting any current and the Unit C4 battery was still isolated. Maybe that'll become clearer in time in a future report. The other point of note here is that the DC bus design intentionally interlocks against closing two battery banks in parallel at the same time. I've watched electrical engineers like me early in my career state that the risks are overblown and there's nothing wrong with doing that, to, in more recent years, people being terrified of paralleling battery strings at all. Why it can be a problem relates primarily to imbalance between the battery banks. All batteries have an internal resistance that changes based on their charge level and battery health, let's say. If you connect a battery with minimal internal resistance, thus lower in charge level or charge capacity, as in you have a damaged cell, for example, to a battery with higher internal resistance and a higher charge level, the charge will naturally transfer from the charged battery to the uncharged battery. The problem is that this transfer of charge in traditional batteries is completely uncontrolled. And because the internal resistance can be quite low, the current can be quite significant, which can rapidly heat cables and bus bars connecting the battery strings, damaging the cells as well, and shortening the battery's life. Whether that current spike is long enough to cause a failure or not is the question. And there are many variables determining battery health that just checking the floating charge level isn't always enough. With traditional lead-acid flooded cells, we would check the specific gravity rather than the float voltages on each cell to better understand battery bank charge level, and if cells within each bank needed servicing or replacement. Thus, in recent years, with fully sealed lead-acid batteries like AGM, that's an absorbent glass mat, and lithium batteries, these have less direct methods of determining their health, and lithium batteries have charge controller circuits to more thoroughly regulate power flow as an additional layer of protection. What's interesting to note is that the Callide B units do not have this design. They do permit temporary operation of their batteries in parallel. Hence, this scenario could not happen at Callide B. Of course, there's no detail about how big the strings were or what kind of batteries were in use. But given the age of the plant, it's highly unlikely they'd be lithium batteries, since in the early noughts, these were still very expensive. Then again, given the original batteries would have been 20 years old at this point, it's also unlikely they were the original battery strings. But there's no information provided about this either. Again, presumably, had they been replaced, they would have been replaced with a like-for-like, and flooded cells have been out of style for various reasons for decades, so AGM lead acids are the most likely option. Having said that, AGM battery manufacturers can prohibit parallel connection and threaten invalidation of warranty if it's ever done, so maybe that was a factor too. There's simply not enough information provided to be certain either way. Let's talk about cooling gas. I just want to touch on the use of hydrogen gas because it's not something most people are aware of with generators these days. Hydrogen gas is commonly used to cool larger turbine generator sets, or specifically the generator. It probably seems like an odd choice. Thank you, Hindenburg, for making everyone afraid of hydrogen, but there's a lot of very good reasons to use hydrogen. Hydrogen has the highest thermal conductivity of any gas, being between 7 and 10 times more effective at thermal transfer than air is, which is predominantly nitrogen. Hydrogen has a very low density, being the lightest element, and therefore presents a very low drag coefficient, and thus doesn't slow down the spinning of the generator to any significant degree. It can be easily detected if there is a leak, and intelligent design can prevent any escaped hydrogen from reaching its lower explosive limit, or LEL. It can be contained effectively using pressurized oil-based sealing systems, and it's cheap to make, at least in the volumes required for this application. For all these reasons, it's the most popularly used cooling system in generators larger than 60 megawatts. In generators around the 500 megawatt range and above, in addition to hydrogen gas cooling, water cooling is often employed in the stator windings to further control the temperature. But I digress. Let's talk about feeds and interlocks. The station main DC bus and each unit DC main bus each fed their own unit DC distribution board buses with an automatic transfer switch, or ATS, sometimes also called, in this case, an ACS for an automatic changeover switch connected between them. Same thing. How the system is supposed to work is that if the unit DC main bus is being fed from the station bus, the DC distribution from that unit can draw power from either the cross-fed power from the station bus directly, or from either the cross-fed power from the station bus via the main bus, or directly from the station bus. But the ACS only allows connection to one at a time. If you didn't ensure that, you'd run the risk of circulating currents between the two different electrical pathways. Hence, the ACS operates as a break before make and auto-senses which bus has power and was configured to prefer the unit DC bus in the original design. For those not versed in electrical engineering jargon, break before make means that any transfer switch consists of two switches or circuit breakers, and they're configured to break the connection, meaning they open the currently closed switch or breaker such that both are open, breaking the circuit, before then closing the other switch or breaker to make the circuit complete again. There are other systems that make before break that are sometimes also called bumpless transfer switches for the opposite reason. But in this case, the ACS was connected to its preferred DC unit C4 bus, and when the unit C4 DC main bus went dead and the station bus still had power, it still did not switch over when it should have. In the investigation, it was found that the ACS automatic changeover component had been damaged in an incident where both Callide unit C3 and C4 simultaneously tripped at 10:57 a.m. on the 13th of January 2021, some 4 months earlier. As a result of that investigation, a design modification to the ACS controller that would have repaired the automatic changeover component damage was scheduled. However, those modifications had not yet been made. Specific details about what the damage was and what the modification was suggested are not available. However, it was at least a known issue. It's worth pointing out that the ACS could have been manually switched over from the switch room at the panel. However, personnel had been evacuated from the switch room at some point after the power loss. The report from CS Energy states, and I quote, "The ACS was available for manual operation but was not operated." End quote. The report isn't clear about why it wasn't operated. We know they evacuated the switch room, however, it wouldn't have been immediately. AMO state in their report that, and I quote, "Due to personal safety risk, AMO understands that operators were unable to physically confirm whether the C4 unit remained online." End quote. This follows the statement regarding the control room, however, presumably refers more so to the switch room and turbine hall. Certainly, there was a fire in the turbine hall at that point, but considering the timeline, loss of SCADA visibility occurred at 1:33 p.m., a fire was reported at 1:40 p.m. In those intervening 7 minutes, the first thing I would expect an operator to have done would have been to go down into the turbine hall to do a visual assessment and confirm the steam valves were open, possibly also the switch room if I was a technician or electrical engineer to check what had power and what didn't. They had plenty of time to do this, but it raises the question, why evacuate the switch room? And if they did, surely they had enough time to trace the power loss before they did. More on this later. Unfortunately, I don't have photos of the switch room. However, I've been in enough switch rooms in the last 30 years to make an educated guess about why they didn't operate the changeover switch. For traditional LV and MV switchboards in the days before SCADA systems, it was quite popular to draw key parts of the electrical single line diagram, or SLD, overlaid on the front of the switchboard. An SLD shows which components connect to what electrically, from transformers to circuit breakers, transfer switches, and destination loads. You can still order switchboards with an SLD mimic printed on the front panel. However, they are more expensive, and with the modular design of switchboards these days, drawing a straightforward SLD can cause headaches for the designer when they're laying out the board. The really fancy ones I've seen in the past go so far as to have green indicator lamps to show which bus is live, the position of the ACS, with lamp indicators that follow the single line diagram on the switchboard. That said, I haven't seen one of those in years. I suspect that with the prevalence of SCADA systems, a decision that's becoming quite common is to not pay the extra for the SLD mimic overlay and to go with the cheaper design, relying on SCADA for remote indication. After all, you can still tell the state of a breaker when you're in front of that breaker, just not what's connected to what else on the switchboard with just a glance. Even so, it's generally required that an SLD is kept on display or accessible within a switch room, and that can be kept in drawers in the room or more commonly displayed on the wall nearby. So the likely reason they didn't switch it manually is that when you're under that kind of pressure, information at a glance is crucial. Tracing a single line on the wall whilst chaos is going on around you, finding the right breakers and determining what's on and what isn't on when you're under immense pressure is much, much harder than you think. This is why it's key to have good local state indication as well as manual override controls. They had the manual controls, but it's unclear if they had good local indication as well and may have hesitated. But there's still something in the CS Energy report that's unclear to me. From the report, it states that the ACS not changing over, and I quote, prevented the recovery of the DC supply to the Y generator protection system. However, even if the ACS had operated, it would not have resulted in supply to the emergency turbine lubrication oil or the emergency sealing oil pump, and therefore it is unlikely that it would have prevented the turbine bearing damage. End quote. There are DC emergency pumps for lube oil and seal oil, but it's not clear if they were connected to the DC main or DC distribution board. If they were on the DC distribution board, they would have come back online when the ACS switched. And if they were on the DC main board, either closing the DC main station interconnector they opened at 1:33 p.m. or closing the Unit C4 DC battery breaker, which should have been almost next on the switching procedure, would have brought the DC pumps back online. Surely they could have. Even if they couldn't, and let's assume the CS Energy statement is true, return of DC power would have provided power to the generator protection Y circuit. So what's that? Well, a bit about circuit breaker power circuits then. Protection circuit breakers often have two sources of DC supply for redundancy, commonly referred to as their X and Y circuits. In the case of the generator circuit breaker that connected the generator to the grid, the X supply came from Unit C4's DC main switchboard, and the Y came from Unit C4's DC distribution board. Had the ACS changed over, the Y circuit would have been live and then allowed the GCB to operate if needed. And here's my quandary. The Callide substation breaker was configured to permit some reverse power flow, since during a plant startup, power flows from the grid into the unit switchboards to provide startup power to the required subsystems. Once the generator is up and running, it syncs to the grid and power flows into the grid, and we're up and running. The GCB, on the other hand, should never have any significant reverse power flow. The GCB should have reverse power protection to prevent the generator from flipping into motoring mode, like it did in this incident. The fact that CS Energy's report says what it does suggests either A, the report is incorrect in this respect, or B, the GCB had the incorrect reverse power protection settings, even if it was energized. So if the GCB did actually have the correct settings for reverse power flow, then it would have tripped the GCB once the ACS changed over. The generator would have had no power to drive it, and it would have stopped rotating. No damage would have occurred, and the grid would have remained stable. Hopefully, what actually happened in this regard will come to light in future. Forgetting the GCB for the moment, the DC power would also have allowed the backup diesel generator to close onto the emergency 415-volt AC bus, thus supplying power to critical systems, thus avoiding the worst-case outcome. Forgetting all of that, they also could have closed the station emergency 415-volt AC bus ties to cross-feed the unit 415-volt AC board once the diesel Jenny was up and running. But why had we also lost AC power at all? The grid was still there. Well, it's not straightforward, that's for sure. So how did the loss of DC lead to a loss of AC? To understand how this happened, we have to first understand arc flap protection and the basics of minimum operating voltages for trip coils. So let's start at the 6.6 kV feeds first. The 6.6 kV supply goes through a step-down transformer to feed the 415-volt bus, and these both power multiple critical subsystems, including the 220-volt DC battery chargers, the generator seal oil pump's primary supply, and lubrication oil pump's primary supply, amongst several other things. These tripped 2 seconds after the station interconnector on the DC bus was opened. They tripped on arc flap protection. So for those that aren't electrical engineers, what does that mean? On larger, medium, and high voltage circuit breakers in a cabinet arrangement, there is normally one or more pressure relief flaps or doors on the top of each breaker that is specifically designed to open in the event of a rapid buildup of pressure inside the circuit breaker housing that is caused by an electrical arc. The arc itself could be caused by any failure of the circuit breaker itself that led to a fault condition, but it doesn't matter what the reason is. The primary goal is to prevent an uncontrolled explosion. Better to have a controlled release of pressure than the pressure have nowhere to go and you get an uncontrolled rupture in an unknown weak point in the chassis. As an additional protection measure, regularly attached to these arc flaps is a limit switch that triggers when the flap opens, and the limit switch, which is normally closed, goes open circuit when the flap opens. This circuit then feeds into an arc flap protection relay from the circuit breaker's battery-backed-up DC source, which, in this case, was the same 220-volt DC source from Unit C4's DC main bus. When the protection relay sees a rapid decline in the DC voltage that it's monitoring, it assumes this is because one or more of the arc flaps have opened due to an arc occurring, and then it trips the circuit breaker, and hence AC power is isolated in that breaker in an attempt to render the entire circuit breaker dead and make it safe. At least that's what's supposed to happen. But what happens if the battery-backed-up voltage drops without there actually being an arc? The arc flap protection relay was set to trigger a protection trip if the voltage dropped below 164 volts DC, which is 75% of the nominal 220-volt DC. Keep in mind, though, that the protection relay is also powered by that same 220-volt DC power source as the trip relay that actually opens the breaker. So when the 220-volt DC source voltage drops below 60 volts DC, although the video states 80 volts DC, the protection relay will power down and cease to function. So when the 220-volt DC source voltage drops below 101 volts DC, the trip function itself will no longer work, even if it's commanded to. This is because the voltage at that point simply isn't high enough to create a strong enough magnetic field to physically move the actuator that trips the circuit breaker's trip mechanism. Right, so now let's circle back to why the DC bus voltage decay took 2 seconds. As mentioned earlier, the DC bus voltage didn't just instantaneously drop to zero. There's no such thing as instant anything. Magnetic fields take time to collapse, and bleeding out inductance and capacitance is a well-understood electrical reality. What many people don't appreciate is that scale influences this time delay. At home, when we unplug some electrical appliances on the wall, larger devices with large capacitors will continue to illuminate the power LED on the appliance for several seconds after being disconnected, whereas other, smaller appliances for perhaps only a fraction of a second. In this case, the 220-volt DC system was huge, and the battery charges were huge as well, and hence the decay of the DC bus voltage took longer than you might expect. But this wasn't the only factor. Since the station DC battery charger was outputting a higher voltage, the Unit C4 battery charger had already started ramping down its output voltage in response, giving the load to the station charger per its output setting. In the 74 seconds from when both chargers were present on the same DC bus, the voltage from the Unit C4 battery charger had dropped to only 120 volts DC. The trends from the controller show the DC bus voltage peaking at about 240 volts DC, and within 1 second of disconnection, this had dropped to 200 volts, a second later to 80 volts, and 3 seconds later to 10 volts, then to effectively 0 volts following that. Arc flap input activation, as previously mentioned, was set to 164 volt DC, which was reached approximately 1.3 seconds after the interconnector was opened. Of course, it's not possible to power the trip coil to actually trip the breaker without DC voltage to power the trip coil, and we know the trip coil's minimum operating voltage was 101 volts DC. So now we have a race. Can the arc flap input activation voltage and any associated time delay between its activation voltage and subsequent triggering of the trip coil happen before the voltage drops below its activation threshold? And the answer we already know, yeah, it did. The protection relay takes approximately 5 milliseconds to actuate, and the circuit breaker mechanism takes approximately 8 milliseconds. The DC voltage decay between the activation voltage and the minimum trip coil activation voltage took 82 milliseconds. And with a 13 millisecond clearance time required, this gave a time window of only 69 milliseconds. That's really, really narrow. The fact this lined up in that window is very unlikely. So what do we learn from all of this? There's lots of things to learn, really, and more questions, but I'll just focus on 3 things: the arc flap design, the automatic changeover switch, and local indications or lack thereof. I'll start with arc flap settings. The arc flap trigger was 75% of nominal, which is quite high, but not unheard of. Had it been set to something more decisive, like 50% of nominal, based on the trend in the report, then would the outcome have been any different? Well, let's work the numbers and find out. Based on a linear drop of 67 volts DC over 82 milliseconds, that's 0.817 volts per millisecond. Picking an even fraction to start with, at 50% nominal, let's say, the drop would have been only 9 volts from the activation to the trip point, which is 7.3 milliseconds. Now that's right on the line, so it probably would still have tripped, but it would have been very, very close. But we can work backwards, and then we can calculate that at 45% of nominal, it wouldn't have tripped at all. The problem is that for real-world, actual arc flap activation, the voltage drop would have been nearly instantaneous, as the local trip circuit is very small, with minimal inductance and capacitance to bleed out. Hence, there would be little to no difference between a 75% or 25% of nominal setting. Personally, I would have set it much lower than 75%, but opinion is a bit divided on that point. Logically, it would make more sense to set it below the trip coil minimum activation voltage to prevent what happened here, as it should make no difference to the final activation delay by waiting for the voltage to drop another 30%. When looking at this from a HAZOP or CHAZOP perspective, the common mode failure of supply voltage would have guided the decision for that setting. Having said that, it's a design detail I know from experience is debated amongst electrical engineers. Now let's talk about the automatic changeover switch. Now, provided that the GCB was set up correctly, this could have prevented the incident from escalating, but questions remain about the nature of the damage from the 2-unit trip 4 months before the incident and when it was due for repair. Having said that, when you're preparing a work plan for something, it's important to review the work plan before work commences to ensure that the current operational state of the plant you're working on still applies and note any exceptions. If the plan was written several months earlier, and likely a copy and paste from Unit C3s and so on, then it's unclear if a review was undertaken that considered the potential risks of doing these works when the ACS was in manual mode. As I always say, time changes risk, so you need to look at it again before you actually start. Not having a copy of the procedure, I can't be sure there wasn't a call out to use the manual changeover switch under a failure scenario, but the fact it wasn't suggests it wasn't considered. Maybe that's being too nitpicky, but when you're working on critical systems, the more you pre-plan and pre-assess, the less likely you are to have issues recovering when you're in the moment, under intense pressure to make the right decision. And now about the lack of manual indications from safe, observable locations. It almost begars belief that the operators had no way of easily determining if the steam valves were shut or which buses had power without access to the SCADA system. Like Colonial Pipeline, a loss of SCADA meant manual operation was effectively impossible for the majority of their pipeline network. Contrast that with Black Energy in 2015, where the local controls in the Ukraine meant that loss of SCADA had minimal impact to their ability to restore power. So again, I believe that in control systems engineering, we've gone too far the other way in our reliance on SCADA systems for control and operation of our facilities. You should be able to start and stop your plant and perform critical functions without the SCADA system being functional. Local controls and indicators are mandatory to support this, not optional, and people need to stop thinking that just because there are redundant computers with a UPS or battery backup, that SCADA will always be there, because there are many reasons why it mightn't be, and you need to design for the event that it isn't there. Let's talk about the aftermath. In October of 2022, structural issues at the Callide C cooling tower forced Unit C3 offline as well, with a total repair cost estimate for all issues at Callide C estimated at 400 million Australian dollars, that's 260 million US, and climbing. On the 24th of March 2023, IG Power Callide, or IGPC, who had changed their entity name to Genuity Group previously, entered voluntary administration to be handled by Deloitte. Whilst there has been no direct admission as for the reason, it's likely the prolonged return to service of the units at Callide was a contributor. In June 2023, Jim Sawley, the former Lord Mayor of Brisbane, who had been the chairman of the CS Energy Board since 2015, stepped down from the board 4 months before the end of what was his third term in that role, to be replaced by Adam Aspinall. There was some speculation in the Australian Financial Review that his departure was tangentially related to the Callide Unit C4 incident or the prolonged delay of its return to service, but let's not speculate on that. We'll leave that there. On the 18th of October, 2023, the Australian Energy Regulator, or AER, found that CS Energy had breached the national electricity laws, and I quote, by engaging in the activity of operating the Callide C Power Station, a generating system connected to the interconnected national electricity system without being the registered participant or obtaining an exemption from registration, end quote. The AER subsequently fined the company $67,800, well that's 44,000 US, which was promptly paid. Further to this, though, the AER on the 9th of February 2024 commenced federal court proceedings against Callide Power Trading, stating that, and I quote, the AER alleges that CPT, in respect of the Callide 4 generating unit, contravened R4.15A1 and Clause 5.2.5A1 of the National Electricity Rules, NER, on 25 May 2021. By failing to ensure that its plant met or exceeded certain performance standards, and by failing to plan and design its facilities and/or ensure that they are operated to comply with the performance standards applicable to those facilities. End quote. Legalese. If you dig into it, the point is that the generator failed to disconnect under fault conditions, with the choice quote from dot point number 19 of their concise statement being that the, and I quote, generator protection system failed to cause the generator circuit breaker to disconnect the generating unit from the power system as it should have, end quote. Whilst that case has barely started, previously in 2016, fines under this provision totaled over 6 million Australian dollars, that's 3.9 million US, in South Australia for wind farms and their role in a large-scale blackout at that time. In February 2024, CS Energy noted that about 300 million Australian, that's 195 million US, in insurance claims were being withheld by insurance companies pending a more detailed finding being released about the root cause of the incident. In the press conference following the release of the CS Energy report, the CS Energy CEO stated that multiple changes had already been made at Callide C Power Station to address their learnings to date. Firstly, the battery interlocking system that was designed to prevent both battery banks from being connected at the same time has been modified with an additional switchboard, battery, and battery charger to be connected to the DC buses for additional redundancy and to allow batteries to be paralleled, but not chargers. Oddly, they didn't show the updated single lines at the press conference for some reason. Oh well. The ACS repairs and modifications were completed to improve reliability, and it was mentioned that the ACS preferred position was swapped to station DC for each, rather than unit DC buses, to ensure X and Y protection systems come from different battery strings. The arc flap detection circuit was modified to protect against battery switching type conditions, such that arc flap will only trigger if there is also a high electrical current at the time of detection. CS Energy hired another 25 engineers and added more shift operators on site in response to this incident to, and I quote, supplement their engineering capability to make sure that they've got all the right expertise, end quote. I'll let you decide for yourself what that means retrospectively. At the time of recording, Unit C4 at Callide is still not operational, with the return to service date slipping multiple times, and now reportedly, it is expected to be back online in July 2024. I guess we'll see. So what do we conclude? The released reports from CS Energy and AEMO have a good level of detail, but some more in-depth detail remains missing. Whilst the hope is that it'll be included in Dr. Brady's report, currently there is no known release date for it and no guarantee that it'll address my specific questions and that the report will be released in full to the public. If there is more relevant detail to discuss in future, if and when that happens, we may revisit this topic or we may not. Things I'd still like to know include what was the specific nature of the ACS fault? When was the ACS planned to be repaired originally? The settings on the DC battery charger outputs were biased towards station, not the Unit C4 charger. So when were they set this way and for what reason? What were the generator circuit breaker's reverse power protection settings, such that if the ACS had switched and the GCP had power, would it have actually disconnected from the grid as it should have? Why did they design the battery changeover switches differently from Callide B? There's more, but those are the bigger ones. One area of design that fascinates me a lot is when an abundance of caution erodes the integrity of a design under abnormal conditions. I'm not trying to be cryptic, but the choice not to permit the temporary paralleling of batteries was made out of an abundance of caution, most likely, despite the fact that many other power stations, including its sister station, literally across the road, do not. It created a weakness in the Callide C design. They appear to have had time to check the turbine hall to confirm if steam was still flowing, but they didn't or couldn't for some reason. Did they have to evacuate the switch room when they did? Did they have to evacuate the control room when they did? Because they went back inside in the end anyhow. It feels very much like there was an overabundance of caution that led to indecision, hesitation, and potentially second guessing. Beyond the technical cause and effect that led to this incident, PowerLink could have opened the Unit C4 circuit breaker at Calval substation at any time, but wanted clearance from CS Energy to do so, which was never given because the operators had been evacuated at different times, or when they were on site, they weren't sure it was safe to do so for fear the turbine would overspeed due to a lack of information, due to a lack of SCADA, due to a lack of manual indication they could safely observe. Human factors aren't mentioned in any level of detail in any of the currently released reports, so let's hope that Dr. Brady's report sees the light of day and sheds more light of those in due course. The 18-page CS Energy report that was released was considered to be quite thin by many industry experts, though between it and the AEMO report, it's enough to at least describe the key technical elements that led to this incident. And that's enough for some technical learnings. For the most part, just wish there was more detail. One final note. During the press conference on the release of the CS Energy report, CEO Daryl Bassine stated that this incident was, and I quote, an unstoppable sequence of events, end quote. Was it? I'm not really sure that rings true. If you're enjoying Causality and you'd like to support us and keep the show ad-free, you can by becoming a premium supporter. Just visit engineer.network/causality to learn how you can help this show to continue to be made. Thank you. A big thank you to all of our supporters. A special thank you to our silver producers, Mitch Bielger, Shane O'Neill, Leslie, Callan Fredelius Fujimoto, Jared Roman, Joel Marr, Katarina Will, Chad During, and Ian Gallagher. And an extra special thank you to both of our gold producers, Stephen Bridle, and our gold producer known only as R. Causality is heavily researched, and links to all materials used for the creation of this episode are contained in the show notes. You can find them in the text of the episode description of your podcast player or on our website. Causality is a podcasting 2.0 enhanced show, and with the right podcast player, you can choose to stream value and boost with a message if you like. There's details on how, along with a Boostergram leaderboard on our website. You can follow me on the Fediverse at Chidgey at engineer.space or the network at engnet at engineer.space. This was Causality. I'm John Chidgey. Thanks for listening.